I'm Shalini, we working as assistant professor of physics. In this video, I will discuss the topic for the session 32. The topic of this session is flywheel theory and experiment. A flywheel, it is a heavy wheel of large mass provided with an axle passing through its center. Then this flywheel can be fixed to a wall or it can be placed on a table at a convenient height from the ground. Then a peg is attached to the axle of the flywheel. Then a twine thread is taken and one end of the twine thread is attached to the peg. Then it is wound on the axle. Then to the other end of the string, a weight hanger is attached. And to that weight hanger, any desired mass can be attached. Then let us consider the theory of a flywheel. So a flywheel, first a twine thread is taken and a knot is made at one end and that knot is slipped over the peg which is attached to the axle. Then the twine thread is wound on the axle to have a certain number of turns. Let n1 be the number of turns given to the thread. Then to the other end of the string a mass m is attached till it is at a certain height h from the ground. Then when we leave the mass, then it start descending down under gravity, and at the same instant the thread starts unwounding, and also at the same instant of time the flywheel starts rotating. Let omega be the angular velocity of the flywheel as the thread unwounds, and v be the linear velocity of the mass as it descends down, and let the flywheel makes n1 number of rotations till the mass get detached. Once as the mass descends down and once the mass touches the ground, the peg detaches from the ground, and then when the peg detaches from the ground, the flywheel starts rotating with a maximum angular velocity. So first initially when as the mass descends down, let the flywheel makes an n1 number of rotations till the mass gets detached. Then let F be the amount of work done per unit rotation of the wheel against friction. When the mass is at a certain height h, it will have a potential energy. Let mgh be the potential energy of the mass at a height h. As the mass descends down, its potential energy decreases. And that decrease in potential energy is imparted to the kinetic energy acquired by the mass as it descends down, which is nothing but equal to half mv square, and the kinetic energy gained by the flywheel as it rotates with an angular velocity omega which is equal to half I omega square, and also to do work against friction during n1 number of rotations which is equal to n1 into f. Then according to the law of conservation of energy, the equation can be written as, so initially the mass will be having a potential energy mgh. As it descends down, that potential energy is get converted into three parts, that is mgh is equal to half mv square plus half I omega square plus n1 into f. Take this as equation 1. Then after once the mass touches the ground, the peg detaches from the axle of the wheel. The flywheel starts rotating with the maximum velocity. Let that velocity be omega. And due to friction, finally it comes to rest after making n2 number of rotations. Therefore, as the flywheel rotates, it will have energy, rotational energy, and that rotational energy of the wheel is nothing but equal to work done against friction to make n2 number of rotations. So hence we can write the equation as rotational energy of the flywheel is nothing but equal to half I omega square, which is equal to work done to make n2 number of rotations, which is nothing but equal to n2f. Therefore, from this one, f can be written as equal to I omega square divided by 2n2. Let this be equation number 2. Now substituting the value of f from equation 2 into the equation 1, what you will get is mgh is equal to half mv square plus half I omega square plus n1 into f for substitute for f here, which is nothing but equal to I omega square by 2n2. From this one, this is equal to half mv square plus, from these two terms take half I omega square common, then 1 plus n1 by n2. Again, from these two terms, half is taken common, then it is equal to mv square plus I omega square into 1 plus n1 by n2. Or if you take to this side, 2 mgh is equal to mv square plus I omega into 1 plus n1 by n2. Or I omega square into 1 plus n1 by n2 can be written as equal to 2 mgh minus mv square. So from this one, the expression for moment of inertia of a flywheel is equal to 2 mgh minus mv square divided by omega square into 1 plus n1 by n2. Let this be equation number 3. Then calculation of omega. So since here the angular velocity does not remain constant, so after the peg detaches from the axle, the flywheel rotates with the maximum. Well, initially it will have a maximum angular velocity, and finally due to friction it comes to rest. Hence the value of omega does not remain constant. Hence we have to calculate the angular velocity here by taking the average velocity. So the average angular velocity of the flywheel after making n2 number of rotations, it is given by it is equal to initial plus final by 2. Initially it will have a large angular velocity which is omega, and then finally it comes to rest, hence it is equal to 0. So which is nothing but equal to omega by 2. So average angular velocity is equal to omega by 2. Also, we know that omega is equal to 2 pi m, where f is the number of rotations made per second. So, but here, when the peg detaches from the axle, the flywheel makes n2 number of rotations in time t. Therefore, frequency can be written as equal to n2 by t. So, therefore, from this, in this equation, if we substitute f as n2 by t, what we will get is omega is equal to 2 pi n2 by t. So, now from both the equations 4 and 5, that is, we can write the equate the RHS. So, omega by 2 is equal to 2 pi n2 by t. So therefore from this one expression for omega is 4 pi n2 by t. Equation number 6. Now substitute the value of omega in equation 3. So then if we substitute the value of omega from equation 6 in equation 3, what we will get is I is equal to 2 mgh minus mv square divided by 16. So here omega square can be written as 16 pi square n square by t square into 1 plus n1 by n2. This is equal to 2 mgh minus mv square by 16 pi square n2 square by n2 t square. Take LCM here into n1 plus l2 r. I is equal to, again substituting here, v equal to r omega 2 mgh minus r into omega square by 16 pi square n2 by t square into n1 plus n2. After calculating here, so here 2 mgh. This equation reduces to I is equal to 2 mgh minus of m into r square. Again substituting for omega here, it is 4 pi n2 by t whole square divided by 16 pi square n2 by t square into n1 plus n2. After calculating this one, finally what we will get is I is equal to m into GHT square minus 8 pi square r square n2 square divided by 8 pi square n2 into n1 plus n2. So this is an expression for the moment of inertia of a flywheel. Then knowing the theory of moment, that is a flywheel, let us do calculate the experimentally the moment of inertia of a flywheel. For that one, first initially diameter of the axle is determined by using the vernier calipers. Then the radius of the axle is calculated. Then first initially certain mass is attached to the hanger. Note down the mass and also note down the height of the mass from the ground. Then take it to a twine thread. Certain number of rotations are given. Let note down the n1, that is the number of rotation given to the thread. Then when the peg detaches from the axle, the flywheel starts rotating and finally it comes to rest. Note down the number of rotations made by the flywheel till it comes to rest, that is n2, and also note down the time taken to complete n2 number of rotations. So noting the values of m, h, n1, n2 and t, the moment of inertia can be calculated by using this formula. Again, repeat the experiment with a different mass. So, say in the second trial, different mass of different masses attached to the hanger, and in each case, the values of H, N1, N2, and T are noted. Noting the values, the moment of inertia is calculated. Then afterwards, Finally, the mean value of I is calculated, which gives the moment of inertia of a flywheel. This is the experiment to determine moment of inertia of a flywheel. So these are the books which I have referred for this topic. Thank you.